I'm Tyler Akidau. As he said, I work at Google. I've had the fortune of working on a bunch of data processing technologies there, from Flume Java to MillWheel to Cloud Dataflow, and then most recently Apache Beam. I'm a member of the Apache Beam PMC. And this talk is ostensibly a history talk. It's kind of a brief tour through various data processing technologies. The narrative is kind of focused on stream processing, so that will both that means that some of the things I'm going to talk about, I'm going to grossly oversimplify their impact because I'm really just talking about them within that specific scope. Also to clarify, I'm really just talking about the MapReduce sort of family tree of large-scale data processing. We're not talking SQL, we're not talking HPC here, so it's actually somewhat focused. We're going to be covering these 10 different systems here, all of which I've listed with their full Apache name glory, so I don't have to use Apache anymore in the deck. And yeah, so we'll be covering these 10. As you know, this is a 40-minute talk, so you can tell already that I'm not going to have a lot of time to go into great detail on these. Apologies in advance. Through the talk, we're going to be looking at them all on this timeline to kind of put them in perspective of when they happened. I'll have some specific events for each of them too. Because it's such a fast talk, I'm not going to be able to go into details about a lot of the stream processing stuff we talk about. I'll probably say things, if you're not already familiar with all this stuff, I'll probably say things you don't know what I'm talking about. So again, apologies in advance. You might check out a couple blog posts I wrote. They will clarify a lot of those things. If you're more of the video type person, a couple talks by some of my colleagues that are worth looking at. Slava is actually giving the watermarks talk immediately after mine in this same room, so you can just hang around and see it then. Otherwise, here's some YouTube versions. And with that, let's get started. So we're going to start today back in the ancient days of large-scale data processing with MapReduce. So MapReduce came around roughly around 2003, and at the time, Google was doing lots of large-scale data processing, crawling the web, doing these sorts of things, and then lots of other companies too. And pretty much everybody that was doing this, they were building custom systems to do it. And they were rapidly discovering as they built these systems that data processing itself is very hard. This is why we have data engineers and data scientists that this is their job. But then trying to do this in a scalable way at the same time is even harder. And doing this in a fault-tolerant way on commodity hardware is just brutal. And so the idea that they had was, well, if we can take care of those other two in a framework, and then let people focus on just the data processing part, that would make things a lot easier. And so that's what they did. They built this thing called MapReduce. There's a paper. I imagine a lot of you are familiar with MapReduce, but they described the system they built, the use cases that they had, and why it had worked out really well. In case you aren't familiar with what MapReduce does, basically you've got some sort of input data set. You apply some sort of mapping transformation, which is really more or less an element-wise transformation on elements. It also assigns a key. Then these records get shuffled and grouped by keys. And then you run a reduce phase, so it sees this whole group of records, and you can somehow combine those together, sum them up, or whatever's appropriate. As far as the timeline, C++ version of MapReduce came out in 2003. The OSDI paper I mentioned was 2004 sometime. There were Python and Java versions. I've got a whole bunch of random stuff on here that I don't have time to talk about, but the main point I wanted to make with this slide is that there's roughly a decade of intense development went into MapReduce, and it was all really focused on scalability. So I kind of mentioned a couple of the the terasort, petasort, 10 petasort times down there. Google, as they worked on MapReduce, were continually raising the bar as far as scalability and the amount of just raw power in the system. If you want to learn more about that, our official MapReduce historian Marian Dvorsky wrote this blog post on the Cloud blog, kind of telling you some of the steps along the way and some of the stuff that we did in reaching scale like this. And hopefully someday we can get him to write a full history of MapReduce. But for the purpose of this talk, the main takeaways I want you to have for MapReduce is that it brought this notion of scalability and fault tolerance combined with a simplicity of API, so you could focus on your data processing task, but also do it over massive amounts of data. So next up is Hadoop. So Hadoop, this is one of those systems that I'm going to grossly oversimplify the amount of impact it has for the sake of a cohesive narrative. Hadoop came about shortly after the MapReduce paper. There were, let's see, I'll just go to the timeline here. Basically, some folks were writing this web crawler called Nutch. They had built an open source version of GFS, which is what became HDFS. And they thought, this MapReduce idea is exactly what we need for our web crawler. But they just, they kind of wrote a paper at Google. We have no use for a paper. There's no code with that. So they went and they built their own. And again, there's kind of some sorting benchmarks on there. And of course, as you all, I'm sure, are even more aware than I am, there's way more that happened in this whole timeline in the Hadoop ecosystem than I'm alluding to here. All sorts of things like Pig and Crunch and Hive and all of the tools that we all sort of use at a day-to-day basis. And that leads me to, well, actually, before that, real quickly, if you want a real history from somebody who knows what they're talking about, you should read this post by Marco Bonacci. It's a good read. But the main takeaway I want to have for Hadoop, again, sort of grossly ignoring massive amounts of impact that they've had, is this idea of an open source ecosystem. They took this idea of MapReduce, and they made it so that everybody could use it. And then around that just flourished this massive ecosystem that has brought all the great tools that we all use. All right, so that leads us back to the next one. Next up is Flume Java. We actually just call this Flume internally, so if I say Flume, that's what I mean. I don't mean Apache Flume. But Flume Java came out of the successes of MapReduce, and it was founded in the Seattle office, right when the Seattle office opened in 2007. And it really was trying to address some shortcomings that had started to surface as folks use MapReduce more and more. So the first was, if you remember back to that slide about MapReduce, it had this strict map, shuffle, reduce phase, right? So if you wanted to do anything complex, you inevitably ended up needing to write multiple MapReduces. And as a result, then you inevitably needed to orchestrate these somehow because they would fail or something might go wrong. And so people started writing custom systems again to orchestrate these MapReduces. And furthermore, to make them as efficient as possible, folks would take their nice, clean, clear logical code and they'd start hand optimizing it. And so they'd obfuscate their code and end up with something that ran a lot more efficiently, but was a lot harder to maintain and read and understand. And so what Flume Java did was it introduced this idea of a pipeline. And so you'd have these P collections, which is kind of starting with the blue. The blues at the top and the bottom are kind of sources and sinks, and then the arrows between those rectangles are representing these intermediate P collections. And you'd apply transformations to them, these P transforms. And you could describe a complex full pipeline in very clear terms. And then when you went to run it, Flume Java would take that pipeline, written kind of a clear sequence on the left, and it would run it through an optimizer, very much like the database optimizers for queries and things like that. And it would then figure out how to physically execute this in an efficient way. So this might mean squishing together some stages so that they run in the same job. It might mean moving pieces of stages around. We can look real quickly at a couple examples. So the sort of squishing logical stages together. This is like function composition. Basically you've got some operation C followed by some operation D. They don't need to be in separate jobs. You can put them in the same job, and you get massive efficiency benefits from getting rid of the serialization and the network RPCs and things like that. You get a similar effect for siblings that don't need to be in separate jobs. A more interesting form of optimization is combiner lifting. So a very common thing to do is to do a group by key and then do some sort of operation like a sum after it, right? This is that reduction we talked about in MapReduce. Well, if you do that reduction fully after the group by key, you kind of got to send all that data over the wire. But if you have a lot of data coming in, like say you're counting visits to your website by web browser, right? So you're going to have a lot of traffic for Chrome and a lot of traffic for Safari and things like that. It actually makes more sense to do some partial summation on the sender side before you actually do the grouping, and then just send those partial results and sum those up. And this is the kind of thing that folks were doing manually. But if you have a clean, clear API that lets you express these things in a way that the system knows about it, it can actually do these optimizations for you. So you can still write your code in a clear way. It just looks like you're grouping and then summing. But then under the covers, it will kind of slice and dice your code and ship it around and make it optimal. So there's a paper published at PLDI in 2010 that goes into this in much more detail. Timeline-wise, it was founded, like I said, when the Seattle office opened. It was originally Lumberjack was the original project. it was to build a brand new language focused on parallel data processing, but it was shortly realized that it probably would be better if folks just use the language they're familiar with, so hence Flume Java. Flume C++ came out a few years later. The other thing worth noting on here is, so about, when was that? Like 2013, 2014? I don't know, I can't see from this angle. But anyway, Flume Java was added, or Flume was added to NuGler training. So this means every new person that got hired at Google started learning how to use Flume. And this was really the beginning of the end for MapReduce at Google. So the main takeaways for Flume Java is this notion of high-level pipelines that could be optimized then under the covers manually, or not manually, automatically, and then orchestrated, as a sequence of MapReduces, or later on, just the system itself would orchestrate everything. So next up, Storm. So Storm is when stream processing really hit the mainstream, in my opinion. It came out of, let's see, so it came around early 2011. I think it was December 2010. And Nathan Mars was the creator of Storm, and he was at a startup at the time, I think it was called Backtype, and they were trying to do basically low latency processing. They couldn't, there was nothing in the Hadoop ecosystem that worked for them. They were just kind of using message queues and trying to cobble something together and hitting their heads against it a lot and getting frustrated. So he came up with this idea for a more principled system called Storm. And so the great thing was it actually allowed you to do data processing in a principled way, but get low latency. The downside was, in order to make that happen, they kind of threw away some of the strong consistency guarantees that you'd had with systems like Hadoop in the past. So as a result, you couldn't reliably get correct results out of the system all the time. It only kind of gave it at least once guarantees, or sometimes at most once guarantees. So as a result, because what folks really wanted in a lot of cases was low latency results that eventually became correct, we got this thing called the Lambda architecture, which you're probably familiar with. So the basic idea being you've got some input source on the left, you send it through a low latency processing system like Storm that's not giving you correctness, and you get these kind of sort-of-ish but not quite correct results on the bottom. Sometime later, you send it through something like Hadoop, where you actually get these correct results. You somehow merge the two results together, and you're happy, except for the fact that you've had to write your system twice, you're running it twice, and you're figuring out how to merge these results, which is all hassle. But it was, and honestly, a great idea at the time, because it let you get, there was no other way to get this at the time, right? So if you want to learn more about the Lambda architecture, it came out of this blog post, also from Nathan, called How to Beat the CAP Theorem. As a slight aside, I also recommend reading this, Critique of the CAP Theorem, the CAP Theorem kind of talks about these tensions between, consistency, availability, and partitions, or something like that. But it's not really very principled. Martin Kleppmann wrote this great analysis of it, pointing out kind of the holes in it, and then proposing an alternative way of looking at it that actually is much more principled. So anyway, back to Storm, timeline-wise, again, came around 2011. Backtype was acquired by Twitter, I believe. So that's how Storm eventually became associated with Twitter. Twitter used Storm extensively within the company. And then interestingly enough, a year or two ago, we learned that Twitter had difficulties actually getting Storm to scale to the level that they wanted to, and they had built this new system called Heron to replace it. And so we got the Heron paper a few years back. So we now have essentially two versions of Storm that are kind of API compatible, but very different systems. So that's going to be interesting to see how that plays out. But main takeaways for Storm are that it brought low latency data processing to the masses, but with a cost. So it traded off weak consistency and brought with it the Lambda architecture. Next up is Spark. So Spark is another one of these systems that I'm going to grossly oversimplify its impact, because I'm just going to be focusing on sort of the streaming aspect of things. So apologies in advance. Spark came around in, 2010-ish, 2009. And it's built around this idea of RDDs. The RDDs essentially capture the notion of lineage within the pipeline. So at any given stage, the system knows exactly how you got to that point from the sources. And so if something happens along the way and you lose some shard of that, the system can simply go back all the way to the beginning and recalculate. And they'll actually do this in an intelligent way that spreads this out across lots of machines, so it doesn't impact you too much. And they thought, hey, we built this great batch processing system. Why don't we just do this a lot, and then we can make a streaming system out of it? And that's basically what they did. So Spark Streaming was we'll bundle up some input data, we'll run a batch over it, and then when that's done, we'll bundle up some more and we'll run it again, and voila, we're processing data continuously. It turns out this works really well for element-wise order agnostic operations like filtering, just sort of mapping data. Also works really well if you're wanting to window data as they arrive. So as data show up to your system and you want to chop them up into these bunches and then treat that as a window, that works great. But if you care about your data sort of in the context of when they occurred and your data don't arrive in order, which is remarkably common in data sets, then it doesn't work so well for that. And so timeline-wise, Spark came out of AmpLab at Berkeley. The original paper was like 2010. I think the Spark streaming paper was 2012. Spark 2.0 came out last year, and so of course, everything I've said up until now about sort of shortcomings of Spark all applies to Spark 1x. They're addressing pretty much everything that I talked about there as part of Spark 2.0. So it's going to be interesting to see how that all sort of pans out as they add more and more to that. As far as references for this one, the best one that I've come across is Matei's PhD dissertation. So this is 90 pages of Spark goodness, and it just covers like the whole breadth of sort of the original Spark 1x ecosystem, and it's actually a really fantastic read. So if you have a big chunk of time, I highly recommend it. So the main takeaways for Spark from the perspective of the narrative of this talk at least is they brought the power of strongly consistent in-order streaming. So streaming systems that come to be associated with not being able to produce correct values, giving you inconsistent values, and Spark changed that as long as your data came in order. So next up is MillWheel. So MillWheel is Google's original stream processing system, which is the system I've worked on for about 8 years now. Was also founded when the Google Seattle office opened in 2007. And it was really built up along sort of 4 ideals. So one was the latency reduction. We wanted to provide a way to get lower latency results than we were getting with batch systems. 2 was to deal naturally with unbounded data. So you've got this data sets that just continually grow, and you want to be able to naturally process them in some way, not have to artificially chop them up into these finite silos. But those ideas were then combined with this insistence on supporting correctness. So strong consistency was important. We wanted to be able to calculate correct results and build things like billing pipelines that you could rely on. And also dealing with out-of-order processing. Like, it was just very clear that with the distributed systems we were building and using, it was not an option to only support in-order data. It just was not common enough. So as a result, we could support this use case that I talked about of data arrive out of order, but then you do this time-based shuffle and you get them into the right place and you actually can analyze them in the context they appeared. And this is really important too for with the rise of mobile and mobile devices, where folks may be doing stuff on their mobile phones while they're in airplane mode, and it's not until they come back online 8 hours later after they finish their transatlantic flight or whatever that they actually upload stuff to the server. So out of order data is just really common. As far as what MillWheel brought to the table to support out-of-order processing, it was all essentially based on 4 things. Building a system that was architected for correctness, having a strong notion of state for storing these intermediate results in a consistent way within the pipeline. Watermarks, which give you a notion of progress. I'll talk a little bit more on the next slide, and then Slava's talk after mine is going to cover it in depth. And then timers for giving you the ability to delay things later, especially based off of watermarks, so that you could wait to perform some action until you think your input are complete. Touching on watermarks quickly, the basic idea is that it gives you a relation, or defines a relationship between event time when on the x-axis there when your events happened, and processing time on the y-axis, so when the pipeline actually sees them. Again, I don't have time to go on this into detail. Better off staying for Slava's talk. He'll talk more. Otherwise, we also published a paper at VLDB in 2013, written by Sam McVitie, that covered both the consistency aspects of MillWheel as well as the watermarks system. So, timeline-wise, founded. I just kind of put on there when some of these features surfaced. Zeitgeist was the pipeline mentioned in the paper, so that shows when that launched. The only really interesting thing on here was MapReduce mode, which was effectively an option to turn on a micro-batching version in MillWheel. So instead of sending records via RPC, getting this really fine-grained low latency, we had a number of customers that really wanted to deal with unbounded data naturally, but they didn't care about seconds of latency. Like, they're kind of fine with 5 minutes or 20 minutes, but they'd rather have it be a lot cheaper if we could. And so by micro-batching this and being able to buffer up large amounts of data and then process them all at once, which gives you a lot more throughput and performance, they were able to make that trade-off when it made sense for their pipeline. So that was kind of cool. So what did MillWheel bring to the table? So it brought this was sort of the first example that I'm aware of strongly consistent out-of-order streaming processing system over massive scale data. So next up, Kafka. So this is the first time I've had Kafka in this talk, which is somewhat criminal. But so Kafka happened in around 2011. It was developed at LinkedIn, and it came out of really their experiences of trying to build robust stream processing applications and the shortcomings of sort of everything that existed at the time. So at the time, pretty much everything, all these stream processors, if you had multiple stages in a pipeline, like a count stage and a top stage, they'd communicate via this ephemeral data. So they just send RPCs, and there was no, it wasn't written down anywhere. It wasn't consistent in any way. And they said, it'd be a lot nicer if we actually made these streams durable. Wrote them to a log, and then allowed so the producer could write to the log and the consumer can just read from it. And this really brought about three benefits. One is consistency. Your data was now stored durably and persisted, so you didn't have to worry about it being lost. It wasn't ephemeral anymore. It also gave isolation, which is really nice, especially when you're building complex systems. So if you've got, especially when it's multiple teams building them. So if you've got, some team wrote the count operator and some other team wrote the top, and they did a crappy job on the top operator, and it goes down, and data starts backing up. You don't really want the count operator to come down as well. Like, you'd like it to keep running. And so Kafka gives you this ability to buffer up data between stages and deal with systems, the interconnects between them, being able to absorb things, I guess, when issues come up. And then the third thing was it gave you this warm, fuzzy feeling you had in the batch world of being able to replay data. So with Kafka, you kind of start out with these red markers here, kind of show you where you are within the partitions, and you read data and you're processing along, right? And you get to a certain point, and then you realize, well, crap, we wrote our top computation, and inevitably there's bugs in it, right? And so you realize, oh, okay, well, we've been corrupting our data all along. We're going to have to come along, fix the bug, roll out a new version of top, but you don't really just want to pick up where you left off because you just went and corrupted all the stuff that you ran on that version. So what you really want to be able to do is go back to the beginning and reprocess everything. And when you have ephemeral data just going between in your streams, then that's really hard to do. But with things made durable in something like Kafka, you can just pick up again and take off. So that was really fantastic. So timeline-wise, open sourced in 2011. Confluent was founded in like 2014, I think, and they really put a lot of oomph behind it. As a company focused on this, they started talking about streams and tables, which is kind of a theoretical way of looking at stream processing, which is really cool. In 2015, I think, and then Kafka Streams, which is their sort of well-integrated stream processor system within Kafka, came out last year, 2016. References: Martin Kleppmann wrote this blog post back in 2015. This essentially kind of captures the basics of streams and tables. And then Jay wrote another blog post. Jay Krebs wrote another blog post last year when Kafka Streams came out that kind of ties more of the ideas together. So the key takeaways from Kafka was this idea of durable streams that would give you consistency and isolation and replayability. And then this streams and table theory, which is quite interesting. All right, so that brings us to Cloud Dataflow. It's another Google system that I've worked on. So the idea with Cloud Dataflow, which it was originally founded in 2013, I guess launched to GA in 2015. The idea was, we've done this MapReduce and Flume Java and MillWheel stuff, and there's a lot of cool ideas in there. We should really combine them all together and make this into something that we can actually share with the world. And Cloud Dataflow was really two things. It was this unified programming model for batch and stream processing that combined the ideas from like Flume Java and MillWheel together. And it was also a managed service within Google Cloud that could do some really interesting things. So I'll touch a little bit on both of those. As far as the programming model goes, we tried to break down the way you thought about data processing across these four simple questions. So what are you computing? Are you computing sums or histograms or machine learning models or whatever? Where in event time? Do you not care about event time like in classic batch processing? It's just in some big global window, or are you doing in fixed windows? Or are you building up like dynamic data-driven windows like sessions? Once you have these windows built up, when in processing time do you materialize the results from them? Do you just want one result when you think everything's done? Do you want to do the classic batch thing where you wait for your bounded data to all be processed? Do you want to see things, speculative early results as things progress, and then if data show up late, if somebody comes out of the plane and turns off airplane mode, what do you want to do when late data show up? And then lastly, if you are doing producing multiple outputs per window, how do refinements of these results relate to each other? And what this brought was the to address a large suite of use cases without really ever touching your core. The core logic of your pipeline, this summing or histograms or whatever, it really just required a small set of changes. And I don't expect these diagrams or even the code to necessarily make sense. The point here is just that with relatively small amounts of changes, you can really tailor your pipeline to the specific use case at hand across a wide variety of different approaches. We talked in detail about this in the Dataflow model paper that was published in VLDB 2015. And then, so that pretty much concludes like the programming model portion of Cloud Dataflow that I'm going to talk about. The other aspect was the managed service. So the idea there was, you're going to write your pipeline, you'll ship it off to Google, and then we'll run it through an optimizer, kind of like we had with Flume Java, schedule VMs and whatnot, bring it up, and this would all be in a managed service on the cloud. And the cool things that we wanted to do with this were things like dynamic work rebalancing. So you can send your pipeline to us. We're managing everything on the back end, and we'll do things like, stragglers are pretty common in data processing, right? Like you'll get slow machines, or you'll just, because of the shape of your data, you'll think it's been sliced up, initially in an even way, but it turns out, there's like 2 shards there that are really slow. Without this, you have to do things like backups or just sit and wait for things to finish, and you've got these idle workers that are doing nothing. But Cloud Dataflow has this ability to dynamically rebalance things and sort of do a better job of bin packing all the work as you go along. And so that's both enabled by the managed aspect of the service, and also is built into the APIs that we have in there, so that you could actually express things in a way that allow us to do these sorts of optimizations. Timeline for Cloud Dataflow is not terribly interesting. Founded, launched, there's a VLDB paper. Beam is interesting, but we'll get to that later, so I'm going to move ahead. Main takeaways for Cloud Dataflow is this unified batch and streaming model for processing data, built around the what, where, when, how idiom for thinking about data processing, and this managed service that could do awesome, cool things for you and make your life easier. Next up is Flink. So Flink was a relative newcomer on the scene a couple of years ago. Although it had been around for a long time, at least the bits and pieces of it. Came out of various universities in Germany. I threw up here references to a few of the papers that I found were more interesting, the file impact and whatnot. But the project itself was called Stratosphere when it was in the universities. And eventually in 2014, they decided to take it and turn it into an Apache project, which then became renamed Flink, which is German for fast. The really interesting parts of Flink are the snapshots and then the Flink 1.0 release there. So when they added snapshots in I think it was 2015, that was when they really added strong consistency support to Flink. And it's based off the Chandy-Lampert algorithm. The basic idea is that you've got these data streams flowing through the system. They send these checkpoint barriers along with the data streams. And as those checkpoint barriers arrive at various nodes in the pipeline, once they've sort of seen all the barriers from everybody upstream from them, they'll do a checkpoint and then move on. So it provides a nice sort of distributed and relatively asynchronous way of doing snapshots that allows you to have consistency because they've got checkpoints. If something crashes, they just have to roll back to the previous checkpoint and start up from there. But also gives you very high throughput because you're not doing lots of tons and tons of fine-grained writes. You're kind of able to batch up checkpoints into reasonable sizes. They wrote a paper on it if you're curious to read more. But the big takeaways from Flink was really because of adding the snapshot support and because they also essentially adopted the entire Dataflow model for robust stream processing. They became the first truly compelling open source streaming engine for out-of-order data processing. And And the whole industry is essentially moving in this direction now, which is fantastic because it means we all have lots of different choices now for dealing with this stuff. But they were kind of the first ones on the open source scene to really nail this. So last up, Beam. So Beam is the Apache project that I'm involved with. And what is it exactly? So Beam came out of, you remember when we were talking about Cloud Dataflow, I said it was two things. It's this unified model and SDK for writing pipelines and this managed service. So really Beam was, we and some partners, Data Artisans and Cloudera and Talend and others, took that programming model and set of SDKs and donated them to the Apache Software Foundation. This happened February 2016, I believe. And so Beam is, as I said, it's this open source set of data processing APIs. We want to be able to express data parallel, batch, and streaming algorithms across a single unified API. And it cleanly separates your data processing logic from any runtime requirements, any runtime optimizations or things like that. And it provides portability. It supports execution on multiple distributed processing environments. As far as the vision goes, this is kind of what we want things to look like. We've got the Beam model as the core set of abstractions, these the conceptual ideas of how this should all look like. And then those are manifested in a suite of various SDKs. And users can come along and choose whatever language SDK they want, Java, Python, et cetera. And then they can run this on any of the runners that we support. So we'll support a large set of different execution engines, and they can pick the one that works for them. And the system basically provides layers of abstractions that let you mix and match these sort of arbitrarily. And it provides cleanliness within the whole system API for folks building their pipelines, and also for folks that are adding runners or adding SDKs. They don't there's clean layers of abstraction between all of these. The reality of where we are looks a little more like this. So we've got Java SDKs currently. Python is imminent, coming soon. We have runners on the mainline branch for Spark, Flink, Dataflow, and Apex. There's a gear pump runner and a branch, and that lower level abstraction layer for actually abstracting away, calling the user code from the runners is in progress, but also coming imminently. But one question that comes up a lot with Beam is, well, if you're just being this portability layer, what does that mean as far as what you can do with Beam? So one thing is that one thing that could have happened is that Beam could be the intersection of all runners. It could become a lowest common denominator, but that's not what we wanted from Beam. Another option is that it could be the union of all functionality. It could be the kitchen sink. We'll just take everything that every runner can do and we'll throw it in Beam, and that'll be fantastic. But that would actually not be fantastic. It'd be a nightmare and it'd be ugly. And so what we really want it to be is that Beam is going to, Beam is essentially going to set the future for what data processing should look like. It's going to incorporate all the best ideas in the right way, and we intend to add things to Beam that runners don't support yet because it's the right thing to have. And as runners themselves come up with new ideas that are great and worth incorporating, we intend to incorporate those into Beam in the right way, and thus push forward Beam. So we really hope that Beam can work to both provide portability across lots of systems and also help push forward and sort of unify this march towards getting us to the right place and giving the right tools. So takeaway for Beam is that it's a portable standard API for robust out-of-order data processing, and it's within the broader open source ecosystem. So it's sort of playing by the same rules as everybody else and getting that diverse level of contributions and ideas. So that brings us to the end, amazingly enough. So to recap real quick, we looked at these 10 systems, and for the at least the purposes of the narrative of this talk, I postulate that MapReduce brought scalability, fault tolerance, and this notion of simplicity in data processing. Hadoop really launched this idea of the open source ecosystem within big data. Flume Java brought this notion of pipelines that would then be orchestrated and optimized automatically. Storm brought low latency processing to the masses, but at a cost of weak consistency in the Lambda architecture. Spark, giving an example of being able to do stream processing in a strongly consistent manner, albeit over in-order data. MillWheel, an example of strong consistency with out-of-order processing. Kafka bringing this notion of durable streams, giving you that warm, fuzzy feeling from the batch world. Cloud Dataflow bringing along a unified batch and streaming model and this idea of supporting auto awesome features, auto dynamic scaling and things like that. Flink being a first example of fully open source out of order stream processing, and then Beam kind of trying to tie all those ideas together and bring this into a portable runtime that can really push forward the state of the art, which kind of leads to my thesis here. This is sort of a hidden Beam pitch talk, but the future of data processing, streaming and batch, we believe is Apache Beam, and you can then, the choice of runner then is up to you. So that's all I have. Here's all the links if you're curious. Link to the slides, since this is really tiny, is up there. One other thing is I'm writing a book for O'Reilly, due to be out in summer 2017, co-authored by Slava, who's up next, and then another co-worker of ours, Reuven. So you might want to check that out, or maybe not, up to you. And that's all I got. Questions? Silence. Oh no, there's a question. Yes? Yes.
Would the Dataflow be the reference architecture?
So we as Google engineers working on Beam and Dataflow have two hats to wear. One is the Apache Beam contributor hat, where for us, we want Apache Beam to be successful in its own right, regardless of Cloud Dataflow or not. On the Dataflow side, we always aim to have Cloud Dataflow be the best runner possible for Apache Beam, but there's absolutely no reason that we don't necessarily expect Cloud Dataflow to always be the best reference architecture. Like I had said, if somebody else in the ecosystem comes up with a really fantastic idea that Dataflow doesn't support, but it should be in Beam, we'll add it to Beam, and it'll probably be in Beam supported on that runner before it is supported on Dataflow. We have no intention, there's absolutely no intention of it being just whatever's in Dataflow is what is in Beam. Dataflow is as much of a first-class runner as everybody else in the ecosystem, and will play by the same rules, and we expect the whole ecosystem to drive things forward. Yes, sir?
So, have you heard about time make method to go? Time make.
I'm sorry, I can't hear you.
It's a small data-driven tool, time make.
HiMake?
Yeah.
No, I have not heard of that. Sorry. The question was if I'd heard of a tool from Google, you said?
Yes.
Oh, yeah.
So I use that tool. It's very good, but I didn't see any update for that tool.
So can you say the name again?
It's HiMake, HAMAKE.
Sorry. Never heard of it. I'll have to look it up. Any other questions? Yes, sir. Microphone, please.
Are there any plans to build a Kafka Streams runner for Beam?
So specific plans, no, not that I'm aware of. If you would like to help contribute, or if anybody wants to, that's something that could totally happen. So it's not in our immediate short-term roadmap, though. Any other questions? Yes, one over there, please.
Sorry, this is just kind of a gossipy question, but Eric Schmidt's name was on the one of those papers. Was he actually keeping his hand in, or was he just...
It's a different Eric Schmidt.
Different Eric Schmidt.
Any other questions? No? All right. Well, thank you all for coming. Appreciate it.